Now we'll start with our discussion on the architecture of the Open RAN system. So I'll start with the 3GPP versus the ORAN functions or the nodes. Okay. All right. So before we start this topic, I'd like to introduce you the ORAN Alliance. Okay. So the ORAN Alliance is a group of telecom companies that aim to improve the performance and openness of their networks. So they call for more intelligence in the network through information collection of these virtualized network elements. And artificial intelligence and machine learning can be applied to this collected information. So this is the ORAN Alliance. So last week, right? So we studied about ORAN Alliance, and this is just a recap. And ORAN Alliance was formed in February 2018 with the goal of promoting open and intelligent RAN. And this is the second organization driving the Open RAN movement, following Telecom Infra Project. So as mentioned previously, this is coming from the merging of the two main organizations, the CRAN Alliance and the XRAN Alliance. And you can also start to browse, and I encourage you to visit the ORAN Alliance official website. Okay, so I'll share the link with you, and I'll give you time now to, for those who are okay, for those who are working or watching using their PC or laptop, you can try to browse the ORAN Alliance website. Okay, and familiarize yourself with the wealth data, including technical documents and white papers, up-to-date news and announcement, and the list of ORAN Alliance members and details of upcoming ORAN events. Okay, so if you have the time, so you can click the link I provided to you in the chat box, and I'll give you time now to browse it. Probably in a few, with a few minutes. So you can see here in the ORAN Alliance, you can see the different specifications. If you try to browse it, maybe currently right now, if you're browsing it, you can download the different specifications here. If you want to study deeper on the different specifications. And you can also see the different members of the ORAN Alliance here. If you click the membership, okay, so there are also operator members and contributors and academic contributors. Okay, so these are the different members now of the ORAN Alliance. And you can also see the different tech groups, which we will discuss later. So you can see here the work group 1, which is responsible for the use cases and the overall architecture of the work group of the ORAN Alliance, of the ORAN architecture, and up to the work group 11, which is the security work group. In their website, you can also check the ecosystem. Okay, the ecosystem, which you can see the different resources about the software, the PlugFest, okay, the open testing or the OTIC, open testing and integration centers, and the virtual exhibitions. So if you click on the virtual exhibition, you can see it's just like a Mobile World Congress, no, in a virtual way. So you can click one of the components here where you can explore the different topics such as the open interface, the open source, open cloud. Okay, there's no sound, Apple. Now I'm just showing the website. open white box. Okay, I'm just assisting you to to browse the website. Okay, so intelligent control and intelligent management. Okay, so that is the ORAN Alliance. So ORAN Alliance introduce the ORAN architecture. Okay, and the benefits of the Open RAN architecture, the ORAN architecture, are the following. See, ORAN can reduce the capex and opex. Okay, so with the Open RAN interface, eliminate the single factory and facilitate multi-vendor cooperative deployments, thus enabling a more competitive and vibrant supplier system. And of course, open source software and hardware reference designs will also enable faster innovation through a larger ecosystem. And of course, the native cloud feature of the ORAN will also enable of scaling out designs for capacity, reliability, and availability rather than the expensive scale-up designs. And in terms of the OPEX or the operational expenditure, ORAN will also introduce the embedded intelligence in every layer of the RAN architecture and will also leverage the new learning-based technologies to highly automate operational network functions. So it will reduce the operational activities and hence it will reduce the OPEX. The second benefit that the ORAN architecture pose is it is capable of improving the network efficiency and performance. Okay, so the ORAN improves network efficiency with RAN automation. Okay, so even for the most complex networks, ORAN will have the inherent ability to offer this efficient, optimized radio resource management through closed loop control and to enhance network performance and user experience. And lastly, Open RAN can import new capability with great agility. So the keyword is great agility. So it will be easy to import new network capability via easy software upgrade and with native cloud infrastructure. Okay, so these are the three main benefits of the ORAN architecture. If you look at the high level diagram or a block diagram of the ORAN architecture, it looks like this. So we have the orchestration and automation on top. You have the RAN intelligent controller. You have the E2 nodes, which we'll discuss later, one by one. We'll just want you to look at and study, the overall architecture of the ORAN system. And then you have this NFVI platform, which includes the virtualization layer and the COTS or the commercial off-the-shelf server. And you have this ODU and the ORU. And as I mentioned as well, in each part of the architecture of the ORAN, there are responsible working group that handles each component. So the working group are the following. So we have the work group 1. So the work group 1 is responsible for the use cases and the overall architecture. While work group 2 is responsible for the non-real-time RIC and the A1 interface. So the goal is to support the non-real-time intelligent radio resource management and other higher layer procedure like optimization, policy optimization, and AI models to near real-time RIC. Work group 3 is for the near real-time RIC and E2 interfaces. While the work group 4 is responsible for the open front hole interfaces. Work group 5 is for the open F1, W1, E1, X2, and XN interfaces. Then we go to work group 6, cloudification and orchestration. Okay. Work group 7 on the white box hardware. So they specify and release the complete open reference design for supporting decoupled software and hardware platform. Work group 8 is responsible for stock reference design. Work group 9 for the open X whole transport. Work group 10 for operations and maintenance, and work group 11 for security. Okay. Now let's move on to the overall 3GPP specific functions and interfaces and the ORAN interfaces. So this is the high level architecture of the ORAN and contains the network functions such as the service management and orchestration framework, or the SMO. Okay. This one manages the network functions and the O cloud to host the cloudified network functions. So this architecture shows the following and important interfaces. Okay, so one by one we'll discuss the interfaces. Let's start with the A1 interface. Okay, so this is the A1 interface. Okay. So this A1 interface is the interconnection of the SMO, the non-real-time RIC and the near real-time RIC. Okay. Over this interface, the non-real-time RIC performs the policy management, enrichment information, artificial machine learning model updates, and updates to the near real-time RIC. Okay, so if there's any update on the model of the artificial intelligence from the non-real-time RIC, it will forward it down to the near real-time RIC via the A1 interface. Okay. Next, we have this O1 interface. Okay, the O1 interface. You can see the O1 interface, these two. So this is the interface between management entities, the SMO in the service or the service management and orchestration framework, and the ORAN managed elements for operation and management, also known as the FCAPs. Okay, so for management and file management. Okay, so this is connecting from the SMO going to the near real-time RIC. Okay. OCU CP and OCU UP and the ODU. Okay. And OE node B for in case of the LTE. Okay, so this is the O1 interface. Next, the O2 interface. You can see the O2 interface is the interface between the SMO going to the O cloud. Okay, for supporting the ORAN virtual network functions. Okay, so the O2, this is the interconnection. And other interfaces here, that is for the E2 interface. Okay, E2 interface is the connection of the non-real-time RIC going to the E2 nodes. Okay. E2 nodes. So the E2 nodes, so these are the nodes such as the CU, CP, okay, CU, UP, the ODU, and the OE node P. So these are the interconnection of the near real-time RIC to the ODU. So when you hear the word E2 nodes, so this is the collective term for the EO node, OE node B, OCU CP, OCU UP, and ODU. Okay, so these are the nodes now. And then also, of course, we have this open front hole interface, the connection between ODU and the ORU. Okay, open front hole on M plane. There are also 3GPP interfaces involved here. So you can see here, these are the ORAN interface. So these are the interfaces introduced by the ORAN Alliance. Okay. And you can also have this 3GPP interface. So meaning when you look at the 3GPP specifications and look at the LTE configuration or architectures and the 5G architectures, you can see all of those 3GPP interface. So in terms of the ORAN architecture, we are also using this 3GPP interface. I will just clear my screen. Okay. So for X2, okay. So this is the connection of when you see the C, it's a control plane, and U is the user plane. Okay. So when you look at the OCU, this is centralized unit handling the control plane, and this is the one handling the user plane. So there is an X2 interface that is connected to another OCU CP and OCU UP. So it's just like when you look at the LTE or the 5G or the standalone mode, a non-standalone mode. So if you have an LTE here and then another LTE here, so the interconnection of these two in node B, we call it the X2 interface. Okay, so these are the X2 interface. Okay, and if you are using a non-standalone mode, and then you are using the EPC, the evolve packet for here. Okay, so you have the S1. Okay, and if you are using this interconnection with the 5G, you have the XN interface. Okay, instead of the X2, you will use it at the XN. Okay, so if this is a 5G core, okay, 5G CN. Okay, so if it's a 5G CN, we call it the XN interface. Okay, and the connection going to the nodes to the core network is NGC and the NGU, separating the user plane and the control plane. So this is basically connection to the other nodes and going to the core network. Okay, next is the E1 interface. So the E1 interface is the connection between the centralized unit control plane and the user plane. We call it the E1 interface. And the interconnection between the OCU control plane going to the DU, we call it the F1C control plane. And the OCU UP going to the ODU, we call it the F1U. Okay. So it takes practice, no, to familiarize yourselves with the interfaces. So what I encourage you to do is start practicing to draw the network architecture of the ORAN alliance or ORAN architecture. Okay, so those are the interfaces of this ORAN architecture. Okay, next we'll discuss the non-real-time rate. No? So we'll have an overview of the non-real-time rate. So the non-real-time rate, when you say non-real-time, it's a logical function within the SMO. So it's located inside the SMO. Okay, that enables the non-real-time control and optimization of run elements and resources. It also includes the AI, machine learning workflow, including the model training, inference and updates, and then the policy-based guidance of applications or features in the near real-time rig. Inside the non-real-time rig, you can also see the different RApps. Okay, so later on we'll discuss these RApps. Okay, so there's an RApps here. The near real-time rig or the NRT rig. Okay, so this is a logical function that enables near real-time control and optimization of front elements and resources via fine grain. Okay. It also includes the artificial intelligence machine learning workflow, including the model training, inference, and updates. Okay. So this is where you also find what we so-called the X apps. So the X app is an application designed to run on the near real-time rig. So these applications is likely to consist of one or more microservices. Microservices like load balancing, okay, and power saving also in the X apps. And these applications or microservices are at the point of onboarding will identify now which data it consumes and which data it provides. So the application or the X app is independent of the near real-time rate, and it can be provided. This X app can also be provided by any third-party vendor. Okay, and the E2 enables a direct association between the X app and the RAN. Okay, so these E2 nodes. Okay, so that is for the non-real-time rig and the near real-time rig. So later we'll have a thorough discussion on the non-real-time rig and the near real-time rig. And then we have this OCU. Okay, when you say OCU, it's Open RAN, centralized unit. No, so the OCU, this is responsible for the overall control and management of the RAN and provides higher level functions such as the radio resource management, mobility management, and network slicing. So these two. Okay, so they are divided into two: the OCU-CP. Okay, the OCU-CP or the Open RAN central unit or centralized unit control plane. Control plane. This is a logical node hosting the RRC and the control plane of the part of the PDCP protocol. Okay, while the UP or the user plane logical node that is handling the PDCP protocol and the SDAP protocol. Okay, so this is the OCU and CP. Next, we'll go to the ODU. Okay, ODU or the ORAN distributed unit. So this is responsible for the baseband processing functions of the RAN. So it includes probably the modulation, demodulation of signals, okay, channel coding, decoding, and other signals based on the split now that was discussed earlier. And next we have this ORU. The ORU is responsible for the wireless transmission and reception of the radio signals, typically located at the cell site, and can support multiple antennas and radio channels. And if it's an LTE or an next generation LTE that supports the E2 interface, we call it the OE node B. Okay. And last part would be the O cloud. So the O cloud is this is a cloud computing platform comprising a collection of physical infrastructure nodes that meet the ORAN requirements. So it hosts to the relevant ORAN functions. O cloud is the cloud computing platform. Okay, so this is a collection of the physical infrastructure nodes that meet the ORAN requirements. Okay, so to host the relevant ORAN functions. So the near real-time rig, the OCU, the OCU-CP, the OCU-UP, and the ODU. Okay, supporting the software components. Okay, and the appropriate management and orchestration. Okay, so I encourage you to practice drawing this ORAN architecture, so you can be more familiar with this architecture. No? So whenever you're talking about Open RAN, and then we're talking about near real-time rig and non-real-time rig, you will know immediately where are those architectures or components are located. Okay, and the interconnection as well. Okay, so because basically, if we go deep dive on the discussion, like for example, there are instructors that will be discussing the E2 nodes. So in the ORAN architecture, you will not see E2 nodes, no, and then you will be confused if what are those E2 nodes, and the E2 nodes are this part, right? So this is a collective term. Okay. So when you say E2 nodes, these are the nodes involved in that one. And then these connected via E2 interface. That's why it's called E2 nodes. Okay. Now let's move on to the so four functional software elements. Okay. So you have the overall defined overall architecture consists of these four functional software elements. So you have the DU, the multi-rat CU, okay, the near real-time rig, and the SMO with non-real-time rig. So each of the functional software elements is deployed as VNF or containers, as discussed in the earlier topic, to distribute the capacity across multiple network elements with security isolation and scalable resource isolation. Okay, so the run optimization is using the AI and machine learning. So there are two rigs involved here. The non-real-time rig, okay, which is located in the SMO, and the near real-time rig. Okay, so this is the near real-time rig. Okay, so if you look at the simplified version of the ORAN architecture, it looks like this. Okay. So there are cases that you can see that the CUCP and the CUP are in one block. Okay, it can also be termed as a OCU only. Okay, but you can also separate these two in the control plane and also the user plane. Okay, now let's move on to the Run Intelligent Controller, or the RIC. Okay, controllers in the likes of 2G and 3G were responsible for run orchestration and management. So in the 2G, we call the controllers as the BSC, okay, the base station controller. Okay, so and then for the 3G, we call it the RNC. Okay, so radio network controller. So in the previous years, you can see here there is this what we call the BSC. There's a big server-like structure where there is this your 2G, okay, and then this is the BSC. So physically, you can go to the BSC, no, and the control function is basically located here. Okay, and it holds a lot of BTS, no, or base transceiver station, BTS. Okay, so this is what the GSM or GRAN edge architecture looks like in the RAN. When it comes to a UMTS, the BSC becomes the RNC. Okay, and then this one becomes the node B. Node B. Okay, node B is the node B. Okay. Now, when LTE started, there's no separate control element. Okay, the control mechanism goes to the node B. Okay, and to simplify the architecture and allow faster response time. Okay, in the case of the 5G, the RIC in the 5G Open RAN, we're talking about Open RAN, enables the eNode B, GNode B functionalities for network intelligence, resource assurance, and resource control. Okay, so nawala yung ano dito. Nawala na yung physical controllers like BSC and RNC. You can see it in the eNode B and the GNode B itself. When you look at the architecture of the eNode B, I think it's also here. Mm, yep. So when you look at the architecture of the LTE, it goes directly, no, to the core network. So the access network goes to the core network. So previously, in these 2G and 3G are connected to the CS core and the PS core. No? Okay, CS core and the PS core. Okay, so like this. So right now in the 4G and LTE, this function was removed and transferred, no, to the E node B and the G node B. So when you look at the architecture right now, so you have the EPC, and then directly the nodes. Okay. So the controller part are transferred already here. Also for the 5G core network. Okay. So this is how the controller becomes apparent in the different technologies. Okay. Now the introduction of the RAN intelligent controller, or RIC. Okay. So since the 5G applications require low latency. Okay, so the 5G specifications requires the NFV and SDN to enable configuration, optimization, and control of the RAN infrastructure at the edge. So the RIC enables the eNode B or the GNode B functionalities for network intelligence, resource assurance, and resource control. Okay. Um, um, Originally defined for 5G Open RAN, okay, the RIC, and it is also essential to support for interoperability of different hardware, especially for RU servers and software components. It also leverages data analytics and AI platform for better resource management, some optimization applications, including quality of service, slicing, and mobility, and also self-optimization and efficiency. So the RAN intelligent controller, it consists of non-real-time rate controller, as I mentioned earlier. So the non-real-time rate is supporting tasks that require greater than 1 second of latency. And the near real-time rate, or the near real-time controller, support latency of less than 1 second. Okay. So the non-real-time functions, this includes service and policy management, RAN analytics, and model training for the near real-time rig. Okay, so let's see the non-real-time rig first. Okay. So it is similar to element management if you're familiar with the EMS and analytics and reporting functionalities in the legacy network. It's the non-real-time rig. So the non-real-time intelligent controller, okay, so this is located inside the SMO, or the service management and orchestration framework. It includes configuration management, okay, device management, fault management, performance management, and lifecycle management for all network elements in the network. And all new radio units are self-configured by the non-real-time rig. So it reduces the need for manual intervention, which will be the key for 5G deployments of, example, massive MIMO and small cells for densification. So the primary goal of the non-real-time rig is to support intelligent, no, so there's a word, no, intelligent RAN optimization by providing policy-based guidance, model management, and enrichment information to the near real-time rig so that the RAN can be optimized. Typical example is that the operators can provide policy-based guidance policy like for all. This is typical example now of a policy that they can define in the non-real-time rate. Now, for all voice calls or VoLTE calls, it can be handled by macro site with low band. And for the EMBB connections like data or downloading or uploading services, it will go to the small cells. So that is the sample of policy, that they can define in the non-real-time rig. And the non-real-time rig is also using some what we call the enrichment information. No? So it has different input to train the artificial intelligence and machine learning. And as you can see as well, the SMO and the non-real-time rig is also connected, getting feedback, going to the ORU, okay, and the ODU, okay. So it's and also to the OCU and OCP. So it is using the different analytics coming from these E2 nodes, to train the artificial intelligence machine learning. Okay, so after the policy is already configured, and it's also getting feedback to the E2 nodes, what will happen is that whenever there is an objective or goal that we want to achieve, it will bring down the policy based guidance to the near real time rate. So for example, there are parameters that we want to change because certain policies are not being met, okay, or the thresholds are not yet being met. So it will give the policy goes to the near real time rate. So that's why it's more than 1 second, because it needs to process the different feedbacks and enrichment information coming from the E2 nodes. Okay, so it will bring the policy going to the near real time rate, and the near real time rate, since this is the latency of less than 1 millisecond, it will impose the policy to the E2 nodes. Like for example, the near real time rate will tell to the OCUCP that change parameter. This one change the threshold, okay, so that we can meet the objectives or the policy guidance set in the non-real time rate. So after it is being applied or change the parameter of the ODU or ORU, it will also give back to the feedback going to the non-real time rate. So the non-real time rate will check if the parameters are okay now or still need some tweaking or changing. So that's one of the fundamental procedure in the involvement of the non-real time rate, near real time rate, and the ODU. And that is based on the one application or use case in the load balancing, or balancing the network load between the macro sites and the pico sites or the small cells. Okay, so that's the near real-time rate. Okay. Now we go to non-real-time rate. Now we go to the near real-time rate. Okay, so near real-time rate. So the near real-time rate or the near RT rate is in near real time. Okay, so it includes microservice based software platform for hosting microservice based applications. We call it the XApp. Okay, XApp. Okay, and as I mentioned, XApp can be provided by a third party vendor that develops this kind of software. Okay, so the near real-time rig software platform provides this XApp, which is a cloud-based infrastructure for controlling and a distributed collection of RAN infrastructures. So as part of the software infrastructure, it also provides the northbound interface for operators, such as the A1 interface, connection to the non-real-time rig, and the O1 interface, no, for the non-real-time rig for the management and optimization of the run. Okay. So if you will look inside the near real-time rig, it has a lot of components. No, so there is the A1 in termination, okay, the O1 termination, and you can see here the X app application. So there's a lot of X app that is being developed right now. So one of the developers of X app, if you are familiar with Remedo Labs, so they are also one of the X app that develops X app. So you can see that there are X app for load balancing. Okay. There's also X app for power saving. Also there's X app for different applications such as the unmanned aerial vehicles, okay, and run sharing. Okay, so there are different X apps now. So it depends on the objective that you want to achieve inside the using the Open Run architecture. Okay. As part of this and also the near real-time rig also provides the southbound interface. No, so southbound interface means the E2 interface going to the E2 nodes. Okay. Okay, can we get a quick recap? What are the examples of the E2 nodes? Can you type in? Maybe you are feeling sleepy right now because we're talking about architectures. Can you type in what are the examples of the E2 nodes? Okay. E2 nodes, can you type into the chat box? In the chat box. Okay, we have the OCUCP. Okay, very good. OCUUP, the ODU. What else? Meron pa tayo isa. OE node B. Yeah. Okay, very good, no? Self-optimization is responsible for necessary optimization related tasks across different runs utilizing available run data, no, from all run types like macros, massive MIMO, small cells. And as I mentioned, near real-time rig host, no, one or more X apps, okay, and use the E2 interface to collect near real-time information on the UE, like for example the UE basis or cell basis. So it can collect real-time information. Okay. And the near real-time rig, okay, near real-time rig, okay, control over the E2 nodes is steered via the policies and the data provided via A1, okay, from the non-real-time rig. So as I mentioned, he gets the policy guidance, okay, policies and data given by the non-real-time rig, and then use the X app, no, to have the specific parameters that the E2 nodes will follow. Okay. Okay, so for example, the radio resource management function allocation between the near real-time rig and the E2 nodes is subject to the capability of the E2 node and is controlled by the near real-time rig. So like for a function exposed in the E2 service model, okay, the near real-time rig may monitor, okay, monitor. It can also suspend or stop and override or control the node via non-real-time rig enabled policies. See, so there are functions that can be monitored. You can also only monitor, can also suspend or stop, and override. Okay, so if you already have this kind of parameters defined in the E2 nodes, it can override also. Okay, to meet the guidance set by the non-real-time rig. Okay, so this improves the user experience and increases network resource utilization. So this is the key for consistent experience on the data-intensive 5G networks. So if you will compare it to the current scenario right now, if you're familiar with optimizing a network, for example, load balancing scenario, you want to balance the different loads, no? The different loads from different. Let me just draw something. If you want to balance the load, no, like for example, you have a macro site here, which has a coverage, and then you have a small cell here. Okay, like this. And then in the macro, you have low band, as I mentioned, like for example, 900 megahertz. Okay, 900, not 960. And then you have a high band here, which is, let's say it's 2100 or 3500 megahertz. Okay. So if there is a user here and the user would like to have a voice call, okay, a voice call. So the loads or the policy, as I explained previously, the policy could be for voice call, it would go to the low band. Okay. So the E2 nodes now will also try to give feedback to the non-real-time rig to get this to train the artificial intelligence machine learning to handle this kind of scenarios. So if the user is would like to go for voice call, it will go to this um, low band macro site. And once the user wants to do EMBB, okay, or MBB or EMBB or data, it will go to this small cells. Currently, if you're an optimization engineer, you will do it. If you don't have this kind of mechanism, most of them are creating this as a manual, no? Changing of parameters. So you change the threshold, okay, change the priority, okay, change the priority of the cell, and then based on the threshold of the signal level, you will change it. And then what will happen after that, you will observe the KPI, okay, observe the KPI. If there's an improvement, if there's no improvement, go back to the parameter, change the parameters again. But this time, using the RAN intelligent controller, it is being done by the XApp, the artificial intelligence machine learning, and then it gets the feedback. It's just like not to discourage everyone. It's trying to replace this kind of manual activity. Okay, it makes it faster and more efficient. Okay, using the artificial intelligence and machine learning. Okay. Okay. And one more thing is that, for example, a typical example is QoS prioritization. QoS. Let's discuss the QoS. I'll delete this again. I'll just give you a typical example. No? QoS, quality of service. Quality of service. So QoS is just like a different prioritization in the network. Okay, different prioritization. Let me QoS. Sorry, I'm writing with using my mouse now. My pen is not working. QoS. So quality of service. So giving different prioritization in the network. As we have discussed in the previous sessions, like in the dynamic spectrum sharing, remember that topic? So frequency or the spectrum is just like a highway. Okay, it's just like a highway. It's like a road. So we share the road, right? So a lot of users are here, So using the spectrum to transfer data from point A to point B, right? Or from point B to point A. So it's just like a road. Okay, the spectrum is like a road or a highway. Okay, this is the frequency. Okay, so this is the road. So there are times that the road becomes congested, right? Congested. A lot of users are here, or a lot of traffic is happening inside the road, right? Especially if it's from 7 a.m. to 8 a.m. Okay, we call it the busy hour. Okay, so there's a lot of traffic here, right? So for you to be able to be prioritized in the network, so QoS must be defined. Okay, QoS must be defined. One typical example or analogy for QoS is that suppose there is a lot of congestion happening here, no? And then there's an emergency happen, and then there is this ambulance that needs the resource immediately, right? Can you raise your hand? Can you click the button if you experience like this? Especially if you're the one driving. If you're driving in a congested highway or high traffic road, and then you saw or you see an ambulance coming, what are you what are you supposed to do? No. What are you supposed to do? To be doing? Are you going to block the ambulance? You give way, right? You give way, right? For the meantime, because um there is a possibility that you can still reach your destination. Okay? You will sacrifice time and then you will give some resource, right? You will give a resource to that prioritize service, right? You will give a resource. So yeah, it's glad to know, no, that people will give way. I was not expecting that you will. I do not care. I do not care who's the people inside the ambulance. No? Okay, so you will give way. So this a simple analogy for the QoS, a quality of service. So if there's a service, a typical, like for example, voice call or a special service for emergency team to use the resource immediately, so it will give way to the other to this prioritized network. Like for example, no, there is a CCTV hub. There is a there is a building. Okay, there is a building that has CCTV cameras. So the CCTV cameras, okay, the CCTV cameras are connected. Okay, connected to the network. Okay, connected to the network, right? Connected to the network. And the network is covering this area. Okay, covering this area. So the CCTV cameras are connected to the this eNode B or GNode B, and suddenly there was an emergency. There's a fire. Okay, there's a fire. So for the responders to assess what's happening on the area, so it's easier for them to access the CCTV, okay, to get a video footage of what's happening, right? But there are people here. There are people that is very interested and having fun having fun watching the burning building. It's a once in a lifetime experience, right? So I need to take photo and video of this burning building, right? It just happened. I don't know if it's only in the Philippines, but if someone is someone saw a burning or see a burning building, instead of getting a pile or bucket of water, just activate the phone camera and post it in the Facebook live. Right? Right, live. So what's happening is that these mobile users are also connected, since connected to the same network, same cell, right? Same cell. Now, what's happening is that it's congesting the resources, right? They are blocking the resources. So whenever there is an emergency, it's difficult for the firefighters or emergency responders to access the video, especially if they want an HD, high definition video. So the solution for this one is to use QoS. Okay, so now it gives more importance to this uh, uh, videos, right, or CCTV cameras. It gives importance. It gives more resource than these Tolits and Marites, right? Okay. Yeah. So that's one of the mechanism. Okay, that's one of the mechanism. You give the resource to the CCTV, which is more important than the resource of Marites and Tolits, right? Okay, so that's one of the functionalities, and also you can use it. You can develop an X app to handle this, a QoS based optimization X app. Okay, that is located or homed inside the near real time rig. Okay. All right. So I hope you understand this this analogy of this X app and then examples of the QoS. Okay. Okay. Now let's compare it. Compare the two, the non-real-time rig framework and the near real-time rig framework. Okay. So the non-real-time rig framework is located in the SMO, Service Management and Orchestration Framework. And this one is in the near real-time rig. No? And in terms of latency, it supports greater than 1 second, okay, because they need to get feedback from the E2 nodes, process it, okay, and then analyze it, and then train the artificial intelligence, okay. Now, this one supports task requires less than 1 second, okay, to give down the policy going to the E2 nodes to make it faster, to make it real time. If you want to change the parameter real time, so you need to have a lower latency, okay? And it hosts the R apps. So if a microservice is located inside the non-real-time rig, we call it the R apps. If it's located in the near real-time rig, call it the X apps. Okay. So the R apps for run automation, optimization, such as the configuration management and data analytics. And the host X apps for eNode B, GNode B functionality, such as the radio resource management. Okay, as I mentioned in the example of the QoS and the load balancing. Okay. Okay. Okay, now we'll discuss the relevant interfaces in the ORAN architecture and the need for open interfaces. Okay. Now let's move on to the mobile network interfaces, the front hole, the mid hole, and the back hole. Okay, so we go to the surface level of the interconnections. So the connection between the core network and the BBU currently it's called as a backhaul. Okay, and backhaul could be implemented either fiber optic cables satellite microwave links or terrestrial microwave links. No, how does it happen? Like for example, you have one site here, okay, and then you want to connect another site here, and then this is the core network, okay. So you can interconnect these two, going to this one as fiber optic, especially if there's no problem in terms of infrastructure, or there is no problem in laying out the cables or the fiber optic cables, or it's more cost efficient in terms of using the fiber optic cables. And then of course in the technical requirement, in terms of the backhaul requirement, so the bandwidth of the fiber optic is bigger, right, than the microwave. Now if for example the distance becomes bigger, okay, the distance becomes bigger, okay, or larger, and laying fiber optic cable will be it will incur a lot of cost, okay, bigger costs in terms of the fiber optic, and the transmission requirement is not as big as what the fiber optics can offer. You can use a microwave, okay, you can interconnect it wirelessly, okay, and then going to the core network. This is the core network. Okay. Core network. So this is how we use the terrestrial microwave links. Now, the satellite microwave links is that there are cases. No? There are cases that I'll just delete this. There are cases that due to the location of the site, okay, the location of the site is they call this limited by the curvature of the earth, okay, even though there is a microwave, okay, fiber optic cannot be done because of the distance or the curvature of the earth, or there is a blocking here that even though there's a even we use a repeater here, okay, if we do use a repeater here like this, it will be more costly, and the transmission bandwidth is not that critical. So what we do here is that in these cases we don't use repeater solutions, but we use the satellite. Okay, so the satellite, this one, like this, and going to the core network. So this is how we connect our backhaul. Okay, so this is the connection of the radio access network going to the core network. We call it the backhaul network. Okay. Now what happens in the 5G, where the split or the functional splits are introduced, and the BBU disaggregation is also introduced. So the BBU has been separated or split into two. We have the DU, distributed unit, and the centralized unit. So the BBU previously, so they are separated. So now there is a new interface. We call it the mid-hole. Okay, so previously the mid-hole is not existent. Now there is since this will be physically located, separately located. So there is a mid-hole. We call it the mid-hole, and the connection of the DU going to the RRU is the front hole. Okay, so we have three: the front hole, the mid hole, and the back hole. Okay. Okay. Now let's take a look at the interfaces in LTE. In LTE, okay, so there are different interfaces. So this is a simplified LTE mobile network architecture. So the main concept of wireless telecommunications is to get services, right, from your mobile phone to the specific server. and or from a specific server, you can upload or download, okay, data. So what you will do here is that using your mobile phone, you will be connected to the access network. Okay. So the access network is providing you what we call the air interface. We call it the UU, no? UU interface in the LTE. And then the access network is connected to the core network. So we call it the S1. Okay. The backhaul connection is S1 interface from access network going to the core network. And the core network are it's either hosting or connected to other services now. So this is the interconnection. No, so the two are the UU interface and the S1 interface or the backhaul. Now, if you add more eNode Bs, okay, in the network, okay, so you will introduce, and then you will introduce also the split functionality. So you have the UU interface, okay, the air interface from the RAN going to the user equipment. And then you have the front hole, okay, from the eNode B going to the remote radio head, no? Okay, RRH or the RRU. And the eNode B is still S1. So connection from the eNode B going to the core is called S1. And the interconnection, okay, the interconnection of eNode B to another eNode B, we call it the X2. Okay, X2. S1 going to the core, X2 is to the eNode B. So sometimes even my students get confused on this, no? Sometimes, how do we know if it's S1 or X2? So what I tell them is just like, if this is your core and then you have this 2 eNode B here, okay, and then there's a eNode B here, there are eNode B here. Just imagine there's an interconnection. This is X2, right? You can see the X here. Just to reinforce, right? Just to reinforce that the connection, the interconnection of the 2 eNode Bs are X2. Okay, so you can see the X. Okay, now you will also also remember, right? Even though sometimes it's not logical, but just for you to remember, the interconnection of the eNode B to eNode B is called X2. And how you can say it's S1, no? So the connection of the node B to the core network, okay, core network is S1. Sometimes the connection is not a straight line, right? It's not a straight line. Sometimes it's curved. Sometimes it's curved, right? So we call it the S1. Now you remember, it's S1. Okay. So when you're trying to memorize some interfaces, you need to be more creative, right? You need to be more creative to memorize this and do not interchange it, especially if you're trying to get some certifications. Okay. So I hope you remember this, no? The S1 and the X2. Okay. Okay, and then we have this front hole interface. Okay, so traditional front hole, it uses the common public radio interface, okay, the CPRI protocol, which is generally a vendor-specific implementation. So there are other front hole alternatives. So there is what we call the ECPRI, defined by the ORAN Alliance also. The FAPI and the NFAPI, defined by Small Cell Forum. The Small Cell Forum is a community that built Open RAN with the small cells in mind. No? So they are focusing on the small cells and other Ethernet-based front haul options. So as mentioned, if front haul interfaces are not open, okay, then operators are forced to deploy vendor-locked, okay, upgrades in their RRU and BBU. Okay, let's take a look at the front haul interface. So front hole is the connection of the RU and the BBU. So if the BBU is um, either proprietary or non-proprietary, okay. So the front hole, so there are information flows in three different planes. So there is a user plane, okay, control and management plane, and the synchronization plane, okay. Use cases as per IEEE 802.3. So there is a CPRI over electrical cable. And then there is a CPRI over electrical backplane and eCPRI over optical fiber. So these different use cases could be driven by applications, no? So different applications or capacity needed. Okay. Now let's move on to the FAPI and the network FAPI. No? So FAPI, API, FAPI. Okay, so functional application platform interface, FAPI, is a common standard agreed, okay, between the chipset component suppliers and mobile base station integrators. Okay, so it is an API for hardware components implementing the 3GPP physical layer functions and software stacks implementing higher layer functions, and also allows the SDUs and SEUs from different vendors. And the network or NFAPI or functional application platform interface, this is the interface between the DU and RU of a split 5G RAN small network, or what we call the RAN functional split 6. Okay. So to give you an overview, this is a typical example of small cells. No, so small cells could be what we call the femtocells, picocells, or microcells. No, but generally it provides in building or outdoor services with small coverage. Okay. Okay, so there is also IEEE 1914.3 radio over Ethernet, or the ROE. So this is IEEE standard for radio over Ethernet encapsulations and mapping. So this enables the transfer of IQ user plane data, vendor specific data, control and management, information channels across the Ethernet based packet switch network. Okay. So as mentioned, it depends, no, on your application and including the capacity requirement for this one. X2 interface between nodes. Okay, so still remember this X2 interface supports the exchange of information between the E node Bs, no, in LTE. So it's an optional interface in 4G networks, but essential in seamless multi-vendor and multi-RAN network RAN component. So there's a lot of benefits of the X2, especially if you're using the coordinated multi-point functionality. So it needs an X2 interface. Also, the X2 gives you the following functions: handovers. So handover means transferring from one cell to another cell. Okay. So if you're not familiar with the handover, it's like this. Okay. Suppose you are traveling from one place to another. Okay. And then there is a road here. Okay. Road. And then you're riding your car and then traveling from this point to this point. Okay. If you get in the cell edge of one cell, okay, and going to the coverage of another cell, the transfer of your call going to another, okay, so that you will have a seamless mobility or coverage and mobility. We call it the handovers. In some books, you can read it as handoff, but most of the time it's handovers. Okay, so that you will not lose, you will not do a drop call. Okay. Load management, as I mentioned, so it's either you go to this site or sometimes to this site. Okay, so just to balance the load of the network, so you can ensure experience of your subscribers. Because if a lot of subscribers are contained in one coverage, and then it will overutilize, no, or congest the cell without this load management, the subscribers experience will suffer. So you need to transfer these users into this area. Intercell interference coordination, or the ICC. Okay, so it has it's checking, no, the different interference level, especially in this shaded region where interference is happening, especially for LTE, where LTE is using the same frequency for most of the sites. So interference is very coherent. So the interference coordination is important. And then network optimization, mobility optimization, and updates about eNode B configuration updates, cell activation, and neighbor list. Okay. Okay. Now let's go to the 3GPP interfaces in the 5G NSA. Okay. NSA. So when we say NSA, it means non-standalone mode. Non-standalone mode. So what does non-standalone mode means? No? Ano yung sabihin ng non-standalone mode? So when we review the different modes of deployment of 5G, we have two main deployment options. No, the first one is the standalone. Okay, so for the standalone, or the SA, so this is the holy grail of 5G. So you have the 5G core network, 5G core network. Okay, you have the 5G core network, and then all of those are the 5G node Bs. Okay, 5G. So you are using one technology connected to your 5G core network. So we call it the standalone mode. And then you have some interconnection. So for the standalone mode, why I say that this will be the holy grail? You can enjoy the end-to-end network slicing, the EMBB, the URLC, and the MMTC. Okay, because of the functionality of this 5G core network. Now the non-standalone mode. Non-standalone mode looks like this, no? Below, but it looks like this. You are using currently the operators right now. They are using LTE core network, right? LTE core, which is we call the EPC, Evolved Packet Core. Currently, we have LTE here. So most of the operators, not only in the Philippines, but as well in the other parts of the country, the LTE network is already matured. So a lot of LTE nodes are deployed in different parts of their country, and also in our country. And to deploy 5G in a faster manner and to drive the market to use 5G, there's a mechanism, or there's a deployment options which is easier for operators to implement. We call it the non-standalone. So in the non-standalone, what will happen is that in the existing LTE site, you will connect a 5G node. Okay, it's another BBU, and then you will interconnect these two. Okay, basically it's in one site. No, it's not located separately. In one site, okay, there are two BBUs. So there are 5G BBU and then LTE BBU. So you are connecting this. So you have LTE and then you have a 5G. Okay, so that is what's happening here. So don't interpret this as a separate cell sites. Okay, so it's in the practical application, or the best practices is you collocate the 5G into the LTE cell site by putting separate BBU, or if your BBU is 5G ready, you'll just migrate the LTE to the to the latest BBU. So basically, it's combining these two technologies in one physical cell site. And then you will connect the 5G in your core network. Okay, so this is what we call the non-standalone deployment. Now, in this particular example, we call it the, what option is this? We call it the, can someone in the chat room knows what option is this? Option what? Thinking. Option 3x. Very good. Option 3x. So this is the option 3x. Option 3x. So you can see in the non-standalone mode, there are a lot of different options. Okay. But most of the operators and vendors recommended the option 3x. Okay. So in the Philippines, we're also employing the option 3x. So meaning there is a connection of the LTE and 5G, the X2 core control plane and the user plane, and the 5G is connected to the core network of LTE. Okay, we call it the option 3x. Okay, all right. So now this is the option 3x. So this is a typical example of option 3x. So as I mentioned, it started with the LTE only. So there is a eNode B connected to the LTE core network. Okay. And then the eNode B has an RRU or RUDU. Okay. And then the gNode B is added, connected to the core network. And then there is the X2 interface. Okay. So sometimes you can see that it is using the X2 interface. If it's especially connected to the LTE core network. So you are using the term of X2 interface. Okay. So this is an example of option 3x. You can see here also X2 interface are not open. Okay. So then operators are forced to deploy a vendor locked upgrades of their BBUs. So this is one of the areas where Open RAN is going to be applied. No? So you can interconnect different nodes because of the interfaces, or because of the open interfaces. But currently right now, because the interfaces are locked, okay, vendor locked. So you don't have a choice but to enjoy the current vendors. No? Okay. So let's summarize the mobile network interfaces. So you can see here on the top, the RAN is composed of the, there's an antenna, there's the RRU, the BBU, okay, and the BBU is separated, split into two, the DU and the CU, okay. Now the RAN is connected to the core network using the backhaul network, okay. The DU and the CU is connected using the mid-hole. The DU and the RRU, or the BBU and the RRU, is connected through what we call the front hole. Okay. And the antenna or the radio access network going to UE is connected via air interface. This one is only cable. Okay. So these are the, and the baseband, okay, baseband to baseband, or eNode B to eNode B, we call it the X2 interface when it comes to LTE. Okay, so these are the mobile network interfaces summary. And then when we look at the interfaces of the ORAN architecture, so you have the open front hole, okay, from ORU to ODU. Okay, F1 from ODU to OCU. Okay, that is the F1. E1 is the connection between the OCU-CP and the CU-UP. And the E2 nodes are, the E2 nodes are connected from these E2 nodes to the near real-time RIC. So we call it the E2. Okay. The A1 is the connection from the RIC and the SMO. The O1 is from the ORU to SMO, and the O2 is for the cloud. Okay, so um that's our interfaces, no? Okay. Okay. Now let's get back to our discussion. So our next topic is implementation options and deployment scenarios. Okay, so let's see the example of a traditional deployment. Okay, so this is one example coming from parallel wireless as well. So let me just get my pointer. Okay. So basically, we have the services located. It's either in connected to our core network. Okay, that we want the subscribers would want to access, and then we have the core network, the transport network, and the proprietary RAN software and platforms. So these are the RAN softwares, and we have the corresponding RAN hardware. So these are all also proprietary. So if you look at this could be the remote radio unit, the BBU, okay, and there are also softwares installed in these hardwares, the transport and the core and the service. So this is the typical traditional deployment. So when you compare it with the Open RAN deployment, so the Open RAN deployment will focus right in the radio access network here in this part, not on this transport and the core. So the service provider or the mobile network operator can replace the Open RAN hardware and software easily, no? So that's the main concept due to open interfaces. So there is example from so previously, no? So you have the same set of hardware, okay, here. So what will happen in Open RAN is that there are different vendors coming from each coming with the different hardwares. So there is a vendor A, B, or C. Okay, can be swapped and could still work with the software from vendor 1, or even with new software from vendor 2, and existing hardware should still work. So the main concept is you can have, and the main key topic is you can mix and match. Okay, mix and match your software and to the hardware. But I think in the actual deployment, there's a challenge, right? There is a challenge in doing this. So because of first is you need to coordinate with different vendors, especially if you're the engineers involved here. You need to coordinate, and then you need to get their specific requirements to work together with this one. And then that's the reason why the Telecom Infra Project is hosting some plug fest, no? And some of the companies also, particularly in US or Japan, have these laboratories or test beds where the interconnections are being tested. Okay, so you can see their laboratories that there is a specific DU or CU, and then different radio units are being tested. No, if there will be no problem in terms of interoperability. Okay, so this is the concept of the Open RAN deployment. So you can mix and match the software installed in your COTS and also the hardware. Okay, so in case of the 5G Open RAN, okay, so you can have this the same. Actually, it's the same, no? Almost same. You have the CU. If you separate the BBU, previously you have one BBU here. If you will separate the BBU into two, you have the Open RAN CU, and then you have the DU. So in the CU, you can have a different software running on your COTS server. The same time, also with the distributed unit, you have the COTS server, commercial off-the-shelf server, and then you can have different softwares running on this COTS server, and as well as the RUs, okay, the remote unit connected to the DU. You can also have these different vendors, no, due to the open interface. So let's take a look at the sample of a parallel wireless solution diagram. So parallel wireless is one of the vendors supporting the all G Open RAN. So when we say all G, it's including the 2G, okay, the 3G, the 4G, and the 5G. So they have what we call the all G COTS hardware and software. So we have the RRH, okay. So there is a 2x2, 4x4, and 8x8 configurations. When you say 2x2, there is a configuration of 2T2R. So specifically, you can see two ports here. Okay, so 2T2R. If you have 4x4, you can see a 4-port here most of the times now. And then if you have 8x8, you can see 8 here. Or you can have another RU here with 4. And then you can combine these two to have 8x8 configuration for the RRH. Okay. And then there is a massive MIMO connected to the COTS BBU. Okay. And of course, this RAN is connected to the following platform. It's either 2G software platform, 3G, 4G, or 5G, where you can have this Open RAN controller or network orchestrator or zone in the edge network. Okay. You can also have in the parallel wireless solution, have this VoWi-Fi, voice over Wi-Fi, and Wi-Fi access point connected to the software platform. In their end-to-end solution, including the core, you can see here the interconnections of the different entities or components, like the 2G circuit switch connected for the mobile switching center and visitor location register here. For 3G, you have the packet core, you have the SGSN and GGSN. And for the 3G is divided into two, no? So there is a packet and then there's a circuit switch. So for the circuit, there's MSC and VLR, same as the 2G. And these are connected to the SMSC for the text messages, okay, and SCP. The 4G PC, you have the policy control function and the AAA for authentication, and HLR, where the subscriber subscriber database are located. So HLR, or the home subscriber server. And you have the 5G core. So this is how the end-to-end architecture being proposed for all G network or all G RAN solution by parallel wireless. Okay. So that's the basic concept of the implementation of the comparison between the traditional deployment and the Open RAN deployment. Open RAN deployment for LTE and Open RAN deployment for 5G. So from traditional, you have all the equipment from software and hardware as a proprietary. Now for LTE, you can have different vendors running on different COTS and with the running a different software. And for 5G, which is separated in the CU and the DU, which can also work with different vendors, and also for the hardware. Okay. So in summary, of our discussion, so you have the radio access network, or RAN, consisting of radio and based band units. So the name will be different. So for 2G is GRAN, UTRAN, EUTRAN, and NGRAN. And for the RAN architecture evolution, as discussed by our previous speakers, so happened. So we started from traditional, centralized, virtualized, and the Open RAN. And the Open RAN happened with the disaggregation of the hardware and software components. Okay. So in traditional and centralized RAN architectures, hardware and software are often proprietary. Virtualized RAN, on the other hand, still includes the proprietary hardware, interface, and software running on a COT server. And in Open RAN, all components, including the interfaces, should be open. And in Open RAN, the four main functional components are the DU, the distributed unit, the centralized unit, the near real-time RIC, and the SMO with the non-real-time RIC. In addition, there are several essential interfaces. So the air interface connects the UE to the RU, the front hole connects the RRU to DU, the mid hole connects the DU and the CU, the back hole connects the CU to the core network, and other interfaces are A1, E1, E2, F1, O1, O2, S1, and X.